So if you remember the node concepts in chapter 4, we talk about two-dimensional steady state problems, and we introduce the concept of nodes to solve heat diffusion equation numerically. So you can do the same theory. You can do the same you can apply the same principles in time-dependent problems as well. So let's take a look at this 2D non-steady state heat diffusion equation. So in here, the main idea here, we need to introduce another index, and it is called time index P. So we had M and N. These are positional index. One is with respect to X. The other one is with respect to Y. So now we are introducing another index, P, which is with respect to time. So we are writing down the time derivative at point M and N as follows. So this is the derivation of or definition of the time derivative using the finite difference method. So temperature at position M and N. So let's say this is the position M and N. So we are measuring the temperature at two different times, at time P and at time P plus 1, and dividing it by the time increments, and that is equal to the time derivative. Okay, so that is the mathematical definition of the finite difference method. So now if we utilize this concept, and if we write down all of these terms in terms of index notations, so this is the definition that I just showed you. And for the second derivative of temperature with respect to position, we have this equality, and second derivative of position with respect to y, we have this equality here. So if delta x is equal to delta y, if you select your grid in a way that delta x is equal to delta y, then we can simplify and collect multiple terms in same parentheses. So we will be obtaining t at p plus 1 in terms of the Fourier number and in terms of the temperatures at the previous time. So this is forward time, this is past time. So p past, p plus 1 is forward or future time. So if we know the temperature in the past, we can move forward and calculate the temperature in the future. Okay, so that is the idea here. So if you know the temperature in the past, so we can calculate the temperature in the future. For instance, if you know the initial condition at t equal to 0, and if you like to calculate the temperature at t equal to 5 seconds, so you just repeat this multiple times until you get the proper time. So alternatively, there are equations that are called implicit equations. In this case, we are using a slightly different definitions. In this case, when we express these derivatives with respect to x and y, we are expressing them at a future time instead of the past time. So the main difference between these two cases, in the explicit method, we express these the positional derivatives in terms of the past time. In here we are expressing them in terms of the future times, and then you go through the same derivation here. So implicit here, explicit here. This is past, this is future, this is past, this is future. So you can rearrange this equation, and in this case, so you start from the future and go backwards. So you start from future and you calculate the time in the past. So if you know the steady state temperature at t equal to infinity, so if you want to know what happens, like what was the temperature 100 seconds before, you can use this this method to calculate temperature. Okay. Again, as in the case of chapter 4, we already have tables that summarizes the most common geometries that you can encounter in numerical methods. So we have an interior node, which is the simplest case. So you have both implicit and explicit forms that are given to you. So ultimately, what we need to do when you are trying to analyze these types of problems, you need to set sets of linear algebraic equations, and you need to solve these using a calculator or a computer, and then you will be obtaining temperatures at particular nodes. And what are the geometries that that are analyzed in this context? We have interior node, inner corner, a surface node, and outer corner. Okay, so we have outer corner, surface node, inner corner, and interior node. So I'm not going to keep you responsible for non-standard geometries for this particular topic. Ultimately, the concepts are very similar to the chapter 4, and we have solved multiple examples on the nodes. So this will be very similar in terms of applying the principles.